Hello and welcome to my video, lesson 9.3 on trig identities. And specifically today we're talking about the sum and difference identities. So we're looking at the identities that are listed here. Depending on how you list them, some people list them all the sum together, all the difference ones together. I like to look at it as a tan, cos, and sine combination, because what you can see here is there's a little bit of a pattern. Now, you don't have to memorize these, they're in your formula sheet, but it's cool to notice these little patterns. The sine version, actually I'll just start with that. The sine version, no matter which one it is, always has sine A, cos B, cos A, sine B. So that's always the same. And then what changes is the positive and negative symbol. And you can see that that's actually true for all of them, that it flips it. But with sine, it stays positive. If it was positive, it stays positive. If it was negative, it stays negative. With cos, it was positive, flips to negative. It was negative, it flips to positive. But again, the inside of the statement, everything else stays the same. So it does flip in here. So maybe I'll use a different color for that. I like pink. Let's go with pink. So it flips inside here compared to what it was, but the rest of it stays the same. Okay, tan works the same way. We always have tan A, tan B, tan A, tan B, or 1 plus, 1 minus. And so then the part that's different is down here. So plus gives a plus up here and a negative down there. Minus gives a minus up there and a positive down there. So I like to notice that the signs are both the same except for positive and negative flip. Coses are both the same except positive and negative flip. Tans are both the same except positive and negative flip. Okay, this is a useful set of identities because it lets us solve for angles that are not on the unit circle. So, for example, if we ask this question here, which says express 75 degrees as a sum of two angles, and then determine sine of 75. So normally we wouldn't be able to solve for sine of 75 just from the unit circle, from last unit. We would have to use just our calculator and get a approximate value, a decimal answer, but it's looking for an exact value, so we have to solve this precisely. How can we do that? Well, we need to have 75 as a sum, that means an addition, of two different numbers. So it equals one number plus another number from our unit circle. Now, we know of a couple different numbers. We know 0, we know 30, we know 45, we know 60, and we know 90. And then, all the way around the circle, but those are the standard ones. And so what we can do is add 30 and 45 to get the 75. So you just have to pick two that match to give the 75 degrees. So 30 degrees, 45 degrees gives 75 degrees. Okay, and then determining the exact value, well, what we can say is sine, maybe we'll do a different color, sine of 75 degrees is like saying sine of 30 degrees plus 45 degrees, which means we can go back to our sine sum identity, which is going to be sine alpha, which is 30 in this case, cos beta, which is 45 in this case, plus cos alpha, which is 30, sine beta, which is 45. So here we have our new statement, which is all fine and good, but that means we need to figure out the value of cos 30, cos 45, sine 30, and sine 45. If we can find each of these, then we can solve that question. Well, cos 30 is when it's shorter and longer, so it's going to be the bigger value, so root 3 over 2. Cos 45 is root 2 over 2, and so is sine 45. Those are paired. And then sine 30 is 1/2. So that's what we start with. So we can take those values and plug them in instead of these values. So sine 30 is 1/2. Cos 45 is root 2 over 2. Cos 30 is root 3 over 2. And sine 45 is root 2 over 2. So now we have each of those answers, and we can just simply solve the fractions at this point. So this is going to be root 2 over 4. The other one is going to be also over 4, but it's going to be root 6 over 4. Simplifying this into one fraction, yeah, there's really not much else to do. We can't put those together, so it's going to be root 2 plus root 6 over 4. So this is our final answer. Okay, so again, we can solve these that are not on the unit circle and getting exact values. So go ahead, pause the video now, and try the next example, which is basically the same except in radians. Try it out right now. Okay, so similar sort of idea, except this time it says a difference of two unit circle things. So what we need to have is, we need to understand what all of our different angles are. So our first one is 0, then pi over 6, pi over 4, pi over 3, pi over 2. And then, it continues around the circle. So if we want to have two numbers that when you subtract them gets you pi over 12, then how do we get this value? Well, we need to subtract pi over 3 and pi over 4. Yeah, that'll work, because if you do that, you have to get common denominators, so then you get 4 pi over 12 minus 3 pi over 12, and so you get 1 pi over 12. Okay, so those are our two angles. So now what we can do is, just like before, we can say sine of pi over 12 is our original statement, but we've now split it up into two different angles. So 4 pi over 12 minus 3 pi. Did I do sine? Oh, I want to do tan. For now, nothing is different. We're just writing tan instead of sine. 3 pi over 12. Oh, which is fine, but we're not going to use those. We're going to use the original. So pi over 3 minus pi over 4. Okay, so all that to be said, we're going to use the tan difference, which is the bottom one there at the top. So we're going to have tan alpha, which is pi over 3, minus tan beta, which is pi over 4, over 1 plus tan alpha, which is pi over 3, tan beta, which is pi over 4. Okay, so we've done all of those now, and so we can now try to simplify it. Now, before we simplify it, we're going to do the same thing as what we did before, and we're going to find the tan values. So tan of pi over 3 and tan of pi over 4. So pi over 4 is 1 because it's opposite over adjacent, and it's a 45-degree angle triangle, like balanced on the opposite and adjacent side. The pi over 3 is taller than it is long. So it's going to be root 3. Yeah. Okay, so with those two values now, we can go ahead and finish answering this question. And so this is going to be root 3 minus 1. 1 plus root 3 times 1. Okay, now the times 1 really doesn't matter, so I'll just erase it. And so now what we can do is actually multiply by the conjugate if we want to get a different statement at the bottom here. So we're going to go 1 minus root 3. 1 minus root 3. So multiplying by the conjugate top and bottom. And so at the bottom, we're going to get 1 minus 3. At the top, we're going to get root 3 minus 3. Then we're going to go minus 1. Then we're going to go plus root 3. So all that can simplify to 2 root 3 minus 4 on the top, and then on the bottom minus 2. And so we'll just rewrite this a little bit, and we'll go 4 minus 2 root 3 over 2. And we can simplify that as well. So it's going to be 2 minus root 3. All right. So we can do this with radians, we can do it with degrees, and again, it's useful because it lets us solve things that are outside the standard unit circle. Okay, so here we could do it kind of in reverse as well. These ones are outside the standard unit circle, but if we match one of our statements above, so this is cos minus sine. So cos is the cos version minus sine, so it's going to be plus cos. So we just have to match with one of our identities. So it's going to be cos 40 plus 20, which allows us to get cos of 60. And because it's in that position, the answer is going to be 1/2 from the unit circle, and that's done. Okay, I recommend you pause the video and try the second question on your own. Okay, so this one is a tan 1 with a plus on top, so it's going to be plus tan. So it's going to be tan and then plus. So pi over 2 plus pi over 3. Right? That's what I have to do. Plus, yeah. Okay, now whenever we add fractions or subtract fractions, you have to have common denominators. So this is going to be 3 pi over 6. This is going to be 2 pi over 6, which means this is tan of 5 pi over 6. And in that position, tan is negative, so we'll just put a negative, and then it's pi over 6 version, and so toa, it's root 3 over 1, or actually just root 3. All right. Sorry, misspelt here. Okay, and then we're going to have just 3 last questions where we're going to try to prove these identities using an algebraic approach. So just, follow along, pause the video, try them out yourselves, and then see if you get the right answer. So whenever we're proving, I'm always going to do this little T shape because it helps keep me organized and make sure that I remember that we're not moving things across an equal sign. That's very, very important. The right side is fine. It's just going to be sine x, nothing changes. But the left side is a sign minus inside. So what this means is we're going to have, I think it's sine first. Yeah, sine first. So it's going to be sine of pi cos of x minus sine of x cos of pi. Yeah. Now, this doesn't look good to start because, like, how do we get to this, sine x? Well, the thing is that we know what sine of pi is, and we know what cos of pi is. Well, cos of pi is -1. Sine of pi is 0. So if sine of pi is 0, this whole thing disappears. So, oh yeah, and this is a -1. So what we're going to really have is negative sine x times a -1. Well, that just means it's sine x. So our final statement, left side equals right side. And never forget that final statement. It's very important. Okay, let's keep going and take a look at the next one. So here we have another thing to prove, an identity to prove. What we need to do is go through and try to simplify the different parts. So on the left side, we have a plus and a minus version of alpha. So we're going to do both. So, and there's a plus in between. So it's going to be cos alpha, cos beta, minus sine alpha, sine beta, plus cos alpha, cos beta, plus sine alpha, sine beta. Okay, it got a little messy there, but bear with me here. You'll notice that this one and this one cancel with each other, and there's two of these that are both positive. So there's two of them, so it's 2 cos alpha, cos beta. And at this point, we can already say left side equals right side. All right. One last identity to solve, or to prove, I should say. It's this one right here. Now, let me just say that we always want to take any reciprocal functions and change them into regular functions. In this case, we have cotangent in two places on the right. So we're going to deal with that first, which is cos alpha over sine alpha. And then it's cos beta over sine beta. Now, already that's one thing we can do. Let's take a look at the left side and see if we can change that sine minus statement where it's got b minus beta minus alpha. And so this is going to be sine then cos, right? Yeah, sine then cos, and it's going to be minus. Okay, so it's going to be sine of beta cos of alpha minus cos of beta sine of alpha. Okay, so that's that statement. And we have sine alpha sine beta on the bottom. Okay, so it's looking a little better, but now the one on the left doesn't have like two different fractions. The one on the right has two different fractions. So what we're going to do is get common denominators for the one on the right. So on the left hand, on this one here, we're going to multiply top and bottom by sine beta. So it's going to be sine beta cos alpha. Okay, so we're multiplying top and bottom, so it's going to be sine alpha sine beta. And because we're getting common denominators, we're going to do the same thing on the other one, and it can be over the same denominator. So it's going to be sine, or let's do it the other way around just because it's going to match better. Cos beta sine alpha. And then it multiplies top and bottom, so that's why we have common denominators. And look at that, we have left side equals right side. All right, I hope this video helps you better understand the concepts of sum and difference trig identities. Hope it helped, and good luck.